Okay, we're talking about exponential equations, solving exponential and logarithmic equations. And so I'm looking for a value of x that makes this equation true, that 2 to the x value is equal to 32. And one of the things we'll need to know is about the one-to-one nature of the exponential function. So, for instance, if I told you 3 to the x is equal to 3 to the 7th, then that means that x has to be 7 and nothing else. And so if I told you that 4 to the x is equal to 4 to the 11th, then x has to be 11, right? So when the bases are equal, then the powers have to be equal. If you have two bases that are equal, then the powers have to be equal. And that's what we're going to use in order to solve this. If I have 2 to the x is equal to 32, then what I want to do is make the same base. And so that means here on the left-hand side, the base is 2, and so I need to do whatever it takes to make the right-hand side a power of 2. Well, we know that 32 has 5 2's in it, that 2 to the 5th is 32. And so now that I know that 2 to the 5th is 32, I know that 2 to the x is 2 to the 5th. Right? So I just replace this 32 with 2 to the 5th. And now, if I have 2 to the x is equal to 2 to the 5th, that means x must be 5. The answer is 5. We'll do that for the next couple of problems. And so making sure that we write everything in the same base, and then once the bases are the same, then the powers are also the same. And so here, this is straightforward. 7 to the x is equal to 49. The base here is 7, and so we change 49 to be 7 to the second power. And if 7 to the x is equal to 7 squared, then because of the one-to-one nature of the exponential function, x must be 2. This one is supposedly more complicated. It is not. 6 to the 4x minus 2 equals 36. The base here, both 6 and 36 are powers of 6. And so this means that 6 to the 4x minus 2, and now I need to rewrite 36 as a power of 6. And so 36 is 6 to the second power. And now that the bases are equal, I can then set the powers equal to each other. And so 4x minus 2 is equal to 2. We'll add 2 to both sides. 4x is equal to 4. Divide both sides by 4. X is 1. Four to the x is equal to 8. And so this one is slightly different because the base is not 4, right? Both 4 and 8 are, it's okay, both 4 and 8 are powers of 2. And so 4 is 2 to the second, and 8 is 2 to the third. And so I'm going to change both the 4 and the 8 to powers of 2. And so when I write 4 to the x is equal to 8, I'm going to replace this 4 with 2 squared. I'm going to replace this 8 with 2 to the third. And then the other remark we need to remember is that if I have a power raised to another power, we multiply the exponents. This is 2 to the 2x is equal to 2 to the third. So you multiply the two exponents. And now that the bases are equal, the exponents are equal. 2x is equal to 3. Dividing both sides by 2, x is equal to 3 over 2. Now, what happens when you cannot make a common base? Here's an example. I cannot make 2.75 a power of 10, and so I need to do something else. And so we're going to use the natural logarithm to do that. And so from the last assignment, that's just the ln. Here's the rule we're going to use. Notice that the exponent here is where the unknown value is. We want to solve for that. So what we need to do is bring this exponent out of the power. And in order to do that, we're going to use a rule that we talked about last time. That the natural log of a to a power, you can bring the power in front. That is from the last assignment on exponential and logarithmic properties. So you can bring all powers in front. And so here's how we're going to use it here. 10 to the x is equal to 2.75. Here are the steps. Number 1, apply the natural log to both sides. When you do that, you get the natural log of 10 to the x is equal to the natural log of 2.75. Now, I'm going to call this the power rule. And then, so we're going to use the power rule. And so what does the power rule say? The power rule says that I can bring, if I have the natural log of some number, in this case 10, to a power, in this case x, I can bring the power in front. And this is extremely useful because now I bring the x in front. And this allows me to solve for x. And so now the power has been brought in front, and now to get x by itself, I'm currently multiplying by the natural log of 10. To get rid of it, I just divide both sides by the natural log of 10. And so I'll make that a step. So then divide. And so x is now solved for. X is equal to the natural log of 2.75 all over the natural log of 10. And that is the answer. That's exactly what you put in for part A. That goes there. And then for part B, you put this in a calculator and it gives you the decimal approximation. So let's bring up the calculator. So the answer to part A is the natural log of 2.7 over the natural log of 10. And then for part B, we'll go ahead and put that in. Here's the natural log of 2.75 and divided by the natural log of 10. And it says round to 2 decimal places, 0.44. Okay. I think we do this a couple more times. Here, we go through these same steps. You apply the natural log to both sides. Natural log of e to the x equals the natural log of 7.1. Bring the x in front. X natural log of e equals the natural log of 7.1. And then x is equal to the natural log of 7.1 all over the natural log of e by dividing both sides. Now, what's special about the natural log of e, though, we said last time that natural log of e is 1. So this is the natural log of 7.1 over 1, and you can leave it as that. So the natural log of 7.1, and then we'll get the decimal approximation to that. For part B, natural log of 7.1, I'm assuming you're still rounding to 2 decimal places. Let's just make sure that's right. So the natural log 7.1, 1.96. This one is very similar. What's this thing stuff? There we go. Similar, but a little bit more complicated. So here we'll apply the natural log on both sides. Then we'll bring this entire power in front, 3 minus 8x times the natural log of e equals the natural log of 1905. And then we already said this, that the natural log of e is 1. And therefore, we just have 3 minus 8x equals the natural log of 1905. And then we solve this like we usually would. We're going to subtract 3 and divide by negative 8. So subtracting 3 on both sides, negative 8 is equal to the natural log of 1905 minus 3. We're then going to divide by negative 8. X is equal to the natural log of 1905 minus 3 all over negative 8. And then this negative 8 can apply to the numerator and switches the order. 3 minus the natural log of 1905 over positive 8. And that you can put in for part A, and then you get the decimal approximation for part B. And so for part B, you need to put parentheses 3 minus the natural log of 1905 divided by 8. Again, we're rounding the 2 decimal places, negative 0.57. So this goes here, and then you get the decimal approximation. Here's a logarithmic equation, and then we're just going to solve using the definition. Now remember, we said last time the definition, when I write y equals log base b of x, if I'm trying to solve for x, then I know that b to the y power equals x. That's the definition. So this means that b to the y power is equal to x. And notice how that solves for x almost immediately. And so for this one, 5 to the third power equals x. 5 to the third power equals x. And therefore 5 to the third power is 125. And so the answer is 125. In this case, we write the natural log of x is equal to 2, but remember, when we write natural log, we mean log base e. So it's log base e of x is equal to 2, and we do what we did before. This means that e to the second power is equal to x. E squared is x, and that's what they want here. They want the answer in terms of e. It's e to the second power. And then you can put the decimal approximation for e squared. So e is here, second, e to the second, 7.34, I'm sorry, 7.39, rounded to 2 decimal places. Here, this isn't any more complicated. When I write log base 4 of x plus 6 equals 3, solving for x, well, I know that 4 to the third is equal to x plus 6. 4 to the third power equals x plus 6. 4 to the third is 64. Subtract 6 from both sides. X is equal to 58. Same problem here. 2 to the 6th power equals 4x plus 6. 2 to the 6th equals 4x plus 6. 2 to the 6th power is 64 equals 4x plus 6. Subtracting 6 on both sides, you get, let's make sure, yeah, a very funky 58 is equal to 4x. And then divide both sides by 4. X is equal to 58 over 4, which is 29 over 2. Here you have to use more than just the definition, and we're also going to use something else. Now, remember before we said that if you had 3 to the a power is equal to 3 to the 7, then that meant that a had to be 7. And in general, if you had 3 to the a power is equal to 3 to the b power, then a and b have to be equal. So again, if the bases are the same, then the exponents are the same. Well, in a similar way, if I had log base 3 of a equals log base 3 of b, for the same reason, that means a equals b. So if you have two logs with the same base, you can just drop the logs, just like we dropped the bases. So when we had 3 to the a equals 3 to the b, you can drop the bases and a equals b. But the same reason, if you have log base 3 of a equals log base 3 of b, you can just drop the bases. We're going to employ that rule right now. The other thing we have to remember is that for logs, addition turns into multiplication. So remember last time we said that log a plus log b is equal to the log, 1 log, and it's log of a times b. And so here, we're going to use that right now. So the steps to this, the first step is to combine the logs. The next step is that log of x plus 8 equals the 1 log, and it's the log of 8 times x times 8, which is 8x. Right? So we're just using this rule that addition turns into multiplication. Now we have 1 log equal to another one, and now we can drop the logs. And so x plus 8 is equal to 8x, and now we're free to solve for x, 8 over 7. We're going to do that a couple more times. Here, addition again turns into multiplication. So log of 4x minus 7 is really equal to the log of the product of 5 and x plus 3, because again, addition turns into multiplication. The logs are now on both sides. We can drop the logs. 4x minus 7 equals, distribute the 5x plus 15, and then negative 22 is equal to x. And so now we get x is equal to negative 22, and that is not in the domain of the log. And so here there is no solution. And the reason why that is because for logs, I wish to put this in red. For the log of x has to be positive. No solution. Okay. solve for x. Here's another rule we learned. We learned, and I mentioned it before, log base b of a to the p is equal to log base b, I'm sorry, we can put the p in front, is equal to p times log base b of a. Right, so you can bring the p in front. Well, we can also bring the p back up to the power. So if I have 2 log x equals log 4, then I can bring the 2 up front. So this is log of x squared equals the log of 4. And now we can drop the logs. Right? So this means x squared is equal to 4. And this means x is equal to 2 or x is equal to negative 2. But because of our previous remark that we can't have negative values put into the log, it's only 2. Right? So we rejected negative 2 because we can't have negative values in the log. Here we're going to use a combination of rules. So remember division, we said that log base b of a minus log base b of b is equal to log base b of a over b. Right, so you're going to divide. But first, we're going to bring this power up. So it's log of x to the second by moving the power minus log base 5. Log of 5 equals log of 45. And so division, subtraction turns into division. So the log of x squared over 5 equals the log of 45. And now we can drop the logs. And so x squared over 5 equals 45. And so x squared equals 225. And so x is 15 or negative 15. But again, we're only taking the positive. We're going to finish by doing some applications. Okay, so one of the applications will be solving for t, and we've been doing this, right? So here's a formula for population t years after 2000. What's the population in 2000? That means you put t equal to 0, because that was the beginning. And when you put t equal to 0, it always turns out to be this number. Because when t is 0, that means that you get 21.2 times e to the 0, and any number to the 0 power is just 1, so it's 21.2. Now the question is, when will the population reach 29.8? But that's a function of time, so you're looking for time. So that means you set 21.2 e to the 0.0414 t equal to 29.8, and now we are solving for t. The steps to do this problem are always the same. Okay, so here are the steps. Number 1, divide by 21.2, the number in front. That gives us e to the 0.0414 t equals 29.8 over 21.2. And then 2, we do what we did earlier. You take the natural log on both sides. When you take the natural log on both sides, you get the natural log of e to the 0.0414 t equals the natural log of 29.8 over 21.2. Now the whole point of taking the natural log is that the natural log and e cancel, and you're just left with 0.0414 t equal to the natural log of 29.8 over 21.2. And then finally, so this is simplified log. And then now 4 you divide. And so then t equals a super ugly natural log of 29.8 over 21.2 divided by 0.0414. And so that's going to give us some time. Let's put that in the calculator. So the natural log of 29.8 divided by 21.2, close parentheses, and then I'm going to divide that by 0.0414. So that's about 8 years. So t is about 8. And so this is 8 years after 2008. 2000, and so the answer is 2008 is the answer to their question, the year 2008. We talked about this formula earlier as well. The A equals P times 1 plus R over N to the NT. They give us everything except now we want to solve for T. So we're going to do the same procedure we did before. And so let's go ahead and do this. We're going to invest $15,000. We accumulated $18,000. So it's $18,000. I'll start up here. It's $18,000 equals the amount we put in was 15,000 times 1 plus 0.07 over 4 raised to the 4t. Right, so that's the formula. So this is, let's just make it clear. This is P, this is N, this is R as a decimal, and this is A, and we're looking for T. Okay, so the steps are very much like we did before. You divide by 15,000. 18,000 over 15,000, 3 goes in each one. That's 6 over, well, 3,000 goes in each one. So that is 6 over 5 equals 1 plus 0.07 over 4, so the 4t. And then we apply the log. So the natural log of 6 over 5 equals the natural log of 1 plus 0.07 over 4 to the 4t. Then rule 3 is we're going to move the 4t to the front using the power rule. So then this 4t comes in front of the natural log, and then you get the natural log of 6 over 5 equals 4t, the natural log of 1 plus 0.07 over 4. And then finally, you divide. So you need to get, so it's this t we're looking for, so you divide by everything else. So t equals the natural log of 6 over 5 all over 4, the natural log of 1 plus 0.07 over 4. How are we putting that in? So first of all, we're going to need a natural log of 6 divided by 5 divided by 4 natural log of 1 plus 0.07